Hello everybody, this video is on independent events and conditional probabilities. Now consider two sets, that's omega, the sets of events, some events, let's say from A1 to AN, that's called the state space. The P is the probabilities, these are the numbers between 0 and 1. And if we add all of those numbers, we must have 1. That's the probability space. The state space and the probability space are related to each other. They are one-to-one correspondence between them. So each event and each probability, for each event here, we have a probability here. And for each probability here, we have an event there. So this is AI corresponds to PI. And the connection rule is the PI denotes the probability that the event AI occurs. Shortly, we write P to the AI. Now consider two events, A and B in the event sense. And if we looked at the probability of the union of these two events, that's the union symbol, A or B. So the probability of A or B events occur is equal to probability of A plus probability of B and minus the probability of A intersection B. That's an intersection. So that is the probability of A and B events occurs at the same time. So this one is called the joint probability of the events A and B. Schematically, it will be easier to visualize the concept in our mind that A union B is the whole of this area, in terms of the area of the probabilities will be different, but just to visualize the concept. This is equal to, this is the probability of A, that will be that, and the probability of B will correspond that part. And the A intersection B, as we see, if we add these two, the intersection will be extra, right? So that needs to be subtracted. So the probability function satisfies that. Now this intersection probability, probability of A intersection B is related with the concept of the independency of the events. Let's give us the, that's the definition. The events A and B are independent, depend only if they satisfy this condition. That is the probability of A and B events occurs at the same time is equal to probability A times probability B. Now let's consider this for a few minutes to observe the definition. Now, that is the probability of A event and B event occurs at the same time, right? Is equal to. So this is the probability of A and this is the probability of B. This happens if and only if the A event and B event, the occurrence of A, the occurrence of B is independent. So if occurrence of A or occurrence of B does not affect each other, then we will have the exactly intersection probability. Does it make sense? The probability of A times the probability of B. Probability of A occurs times the probability of B occurs. If these two events are independent, if these two events occurrences does not depend each other occurrences, then the occurrences at the same time will be exactly the product of these two probabilities. Yeah, by looking at this, take some time to understand this concept. But when you looked at this and to think about the independency of occurrency, this will make sense. This concept gives us a conditional probability. So what is a conditional probability? This is a notation, and this notation shows, says, the probability of B given A. In a long term, if you want to say, probability that the event B occurs given or provided that the event A occurred before B. So this means is that probability of A you know that event A occurred, and then you're asking to yourself, what is the probability of B? So that represents this, and it's called the conditional probability. And this equation is a very important equation, is also the Coase bias equality, bias equation. That is, gives the conditional probability in terms of the joint probability. Probability of B given A is the probability of A intersection B divided by probability of A. That means, see, this is A here, probability A here is given, it's happened, and then you're asking yourself, what is the probability of B? That is given by the formula, probability of A and B happens at the same time divided by probability of A. I think it makes sense. Hopefully it makes sense. If A and B are independent events, then we have P, A intersection B is equal to PA times PB. Then this can be replaced by this one. Then we have the PA and PA occurs in numerator and the denominator. They will cancel out each other. Then we will have the probability of B. So if you have two independent events, then the conditional probability is exactly the itself. It does make sense, right? Because A and B are independent events. A occurred or before or after. Since B is independent of the occurrence of A, that should affect nothing. So that's the probability of B. Because the occurrences of A does not affect the occurrences of B, as they are independent. Then the conditional probability of B given A is exactly the probability of B. Now, this is an example. It's a little bit long example, but let's do it step by step. Assume that the following table shows a survey of output. So we have the male and female participants, and some male participants choose the social science to study, and some choose the math science, and the females are as well, social science and math science. So these are the proportion of the or frequencies in your sample data of the male choosing the social science, male choosing the math science, 25%. It's just example numbers. So the social science is 55%, math science is chosen by 45%. So we have 40% males and 60% females. And of course, with respect to the definition of the probability, this sum has to be 1 and this sum has to be 1. So we are looking at these two as a one random variable and these two in another random variable. You can think of that way. And we are asking ourselves whether this data set shows us independency of these two random variables. Right? This set and this set, are they independent? That's the question to answer. So shortcut, let's M for male, F for female, SS for social science, MS for math science is the abbreviations that I'm going to use for the tables to make it more compact. And like the probability of a male is here is 40%. 0.4. These are some example. Probability of the social science is 0.55, 55%. And this one here, these numbers here corresponds to intersection probabilities, right? This one is the M intersection with SS. And this one is F intersection with SS and so on. So the male intersection probability with the social science is 15%. This is what it means. And that is that number here. So this is these are here are intersection probabilities. Okay, question, can we say that the choice of the social science or mathematical science are independent of gender? Informally. In advanced studies, we will see that we need to perform a chi-square test for independency for contingency table. These kind of tables are called contingency tables. Okay, first, our strategy in this example, assume that the events S and SS and MS are independent of the genders, males and females. We construct a new table under the independence assumption. Then we compare the data table that we have and the table that we obtained. And we will try to see whether they are dependent or independent. And this is an informal way of checking the dependency and independency. So, but it explains the concept. So this is why I choose it. So P A intersection B is equal to probability of A probable to B. That is the formula when A and B are independent events. So what we have here, this is our given situation, right? This is the, I think there exists a slide. That should be M here rather than that is M. There's an intersection, right? So this is an intersection probability of PM and PSS. That is the probability of social science. This is a probability of mathematical science. And this is, that's the male, probability of being a male, probability of female, and this area is the intersection probabilities of as I've just said, but I would like to express it in terms of facts. So that's what it is. So if we assume that independency, so what we need to do, we will take these ones and we will multiply them. So in the original, we have different numbers here, but if we assume independency, in order to be able to get these numbers, only thing that we need to do, we multiply these two because of this, right? Intersection probability needs to be multiplication. In this case, right, this times this will give us a theoretical intersection probability. So this times this will give you 0.22. This times this will give us 33%, and so on, right? This times this will give you 18%. This times this will give you the 27%. So this is the table that we obtain under the assumption of independency. So this is the survey output that we have. So all we need to compare these two tables. If the survey output consists of the independent events, then we should have a similar values in this area. These two tables show that the choice of the social science and the math science are not, what I want to say in that moment is that these numbers, 22% to 15%, these are really different and far away from each other. And we see that they are, social science and math science are not independent of the gender, they are dependent. If it was an independent, the survey results will be much more approachable to these ones. Statistically, this is not an explicit way of saying it. We need to apply a chi-square test, but there's another subject to work on it. We will learn later. What is the probability of choosing math science for a female? Now, this is an example of a conditional probability. So choosing a math science, that is the probability of MS, and given F, that's for a female. So given a female, given the condition, which is a female condition, choosing a maths and the probability, that there's a conditional probability of MS given F. By the formula, we have probability of MS intersection F divided by probability of F. We, from our original survey output, we know that MS intersection F, MS intersection F is this number, 0.2. This is what we have here. And the probability of F is this 60%, that is 0.6, that's there. And then we get the number 1/3, that is a 0.3333. So this is how we calculate the condition of probability. And vaguely, this example explains the independency of two events. So that's all I want to say in this video. Thank you very much for watching.